Hello everyone, we are present our project which talk about effect of metal titanium dioxide composite for organic degradation by أصيلة عبد العزيز خلفان الشكري and فاطمة Abdullah Salim Al-Yaqubi with supervisor Dr. Salam Kazim Al-Dawri, University of Nizwa. I'm Asila Shukri and I will start with introduction. Organic compounds are molecules that are carbon-based. There is different of organic compounds in the environment, which come from factory waste and some of them occurring naturally. Some of them are toxic and harmful and considered major sources of pollution. Factories suffer from the coloration issue. Several methods contribute to decomposition of organic materials such as biotreatment, chemical treatment, and photooxidation that we used in our project. The coloration of organic compounds is considered as an industrial challenge toward the environment. It causes to pollution. Science has found an environmentally friendly of a treatment method for the organic materials using titanium dioxide with UV light. But as you know, the UV light or UV rays are harmful to the environment and to humans as well. So many researchers have tried to use normal light with metals top titanium dioxide for safe decomposition of organic matter. The objective of the study is to investigate the ability of titanium dioxide and titanium dioxide doped metals Fe positive 3 and CO positive 2 under UV and normal lights for the treatment of methylene blue, and different conditions being considered such as methylene blue concentration, titanium dioxide concentration, metal doped concentration, and UV light intensity. We used methylene blue to degrade it. Methylene blue is one of the strongest organic material in color. Because of their rich color and slow decomposition rate, they can cause considerable environmental damage if dumped straight into water.
Hello, my name is Fatima Abdullah Yaqubi. I'm going to explain the photocatalytic process part in our presentation. Photocatalysis is the acceleration of photoreaction in presence of catalyst. Photocatalysis over semiconductors involve the absorption of light of energy larger than band gap, which is generated excited electrons and positive holes. The processes and mechanisms of photocatalysis differ. They can be summarized in four following key steps. First, absorption of light to produce electron-hole pairs. Second, separation of excited charge. Third, transfer of electrons and holes to the surface of catalyst. Fourth, utilization of charge on the surface for redox reaction. We have the examples of photocatalytic mechanism of Fe doped titanium dioxide. The first step consists on the formation of Fe positive 2 ions that results by transfer of photogenerated electrons from titanium dioxide to Fe positive 3 ions. Fe positive 2 ions is relatively unstable when we compare it to Fe positive 3 ions because it have half-filled orbital. The trapped charge can be released from Fe positive 2 ions and afterward migrate to the semiconductor surface to initiate the photocatalytic reactions. So in this sense, Fe positive 2 ions can be oxidized to Fe positive 3 ions by transferring electrons to molecular oxygen, which is absorbed on the surface of titanium dioxide to form superoxide anion, which is our highly reactive oxygen species. In the meantime, Fe positive 3 ions can also act as hole trap because the energy level of Fe positive 4 and Fe positive 3 ion is above the valence band energy of n-doped titanium dioxide. Therefore, Fe positive 4 ion can be reduced to Fe positive 3 ion by capturing electron while the surface hydroxyl group transfer into hydroxyl radical. We believe that the electrons and hole scavenger ability of Fe positive 3 ion is the main feature that helps to explain the higher photocatalytic activity observed for our Fe doped titanium dioxide sample. And the same mechanisms happen for cobalt doped titanium dioxide and the mix of iron and cobalt doped titanium dioxide. This is the result that we got it from our project. This is the scanning electron microscopy analysis at different magnifications, 1000, 5000, 10,000. As shown in micrograph, the morphology of the titanium dioxide nanoparticles is generally spherical, and the nanoparticles are agglomerated together to create several nanoclusters. And these are the SEM analysis of Fe doped titanium dioxide material at various Fe positive 3 dopant level, 0.3 gram and 0.6 gram. Also, this are the SEM analysis of the cobalt doped titanium dioxide material at 0.6 gram CO positive 2 dopant level. In addition, these are the SEM analysis of the Fe and cobalt doped titanium dioxide materials at 0.6 gram dopant level for both of Fe positive 3 and CO positive 2. This table consists the data that we got it from SEM analysis for every catalyst. These are the composition graph of catalyst that we got it from energy dispersive spectroscopy. The results of EDS indicate that iron doped titanium dioxide and cobalt doped titanium dioxide are dispersed between the interfaces of the titanium dioxide and or maybe on the surface of nanoparticles of titanium dioxide. And here we have indicate the absorption of methylene blue in solution of pure titanium with different concentration at every 30 minutes under UV spectrophotometers, and the reflection spectra of all Fe doped titanium dioxide using Solgen method and Solgen method, which cancelled at 450 degrees Celsius under both UV and visible light samples. A shoulder appears at around 646 nanometers. These graphs show the absorption of methylene blue in solution samples and these the graph present the absorption in solution samples of Fe doped titanium dioxide using wet impregnation method, also the absorption in solution samples of cobalt doped titanium dioxide using wet impregnation method. In addition, the absorption and solution samples of Fe and cobalt doped titanium dioxide using same method. These samples take under both UV and visible light. These are the reaction rate constants value for all samples, which were calculated from the linear slope and summarized in these tables. These graphs indicates variation of methylene blue concentration with time for all samples. In addition, these are the photocatalytic kinetic degradation graphs for all samples, where use these graphs to determine the reaction rate constant for all samples. The best results we got it as around 65% of methylene blue degraded in the presence of Fe doped titanium dioxide using 1 gram titanium dioxide Solgen method, cancelled at 450 degrees Celsius under visible light. Around 50% of methylene blue degraded in the presence of the 0.6 gram cobalt titanium dioxide under visible irradiation, and 47% of methylene blue degraded in the presence of 0.6 gram Fe and 0.6 gram cobalt doped titanium dioxide under visible irradiation.
Thank you.